Have you ever peered inside the incredibly fast chips that power your phone or computer and wondered, well, how on earth do different parts manage to work together when they're all running at, wildly different speeds?
Yeah, it's a great question.
It's sort of like trying to conduct this grand orchestra, but each section is playing to its own unique time signature.
Exactly. It's a fundamental challenge facing digital designers every single day.
Right?
And that challenge brings us directly to the heart of this deep dive. Clock domain crossing, or CDC.
CDC.
And this isn't just some minor technical hurdle you see. It's the absolutely crucial process of making sure signals can move reliably, coherently between these different, let's call them time zones, inside a single chip.
Different time zones on a chip. I like that.
So our mission today is really to pull back the curtain on why CDC isn't just a niche issue, but it's unavoidable, it's fundamental, and frankly, a critical challenge in modern digital design. And we'll explore the ingenious solutions engineers have developed to conquer it.
And to guide us through this pretty complex landscape, we've gathered, a comprehensive stack of sources. We're talking foundational articles, cutting-edge research papers, even real-world industry notes that really peel back the layers of this fascinating topic. All right, let's kick things off right at the beginning then. When we talk about a clock domain inside a chip, what exactly are we defining? And maybe more importantly, why can't we just stick to one single universal clock for everything? Like, in the old days, what changed?
Right. So a clock domain is basically a distinct section of a digital design that operates under the control of a single clock, or sometimes clocks that are directly related.
Okay.
Like, say, a 10 millihertz clock and its perfectly synchronized 5 millihertz derivative. That's one domain.
Got it.
The real complexity arises when you introduce multiple clock domains. Now you're talking sections driven by clocks that are unrelated.
Unrelated, how?
Well, maybe different frequencies, or they come from entirely separate clock sources, or perhaps even identical frequencies. But their phase relationship is, unpredictable. And the shift from those older single-domain systems to these multi-domain behemoths wasn't really a choice. It sort of became a technological imperative in modern system-on-chip, or SOSAC, architectures, and also FPGAs.
An imperative, huh?
Yeah. Historically, simpler chips, they could get away with one clock. But as chips got more complex, faster, physical limitations became a huge roadblock.
Physical limits? Like what?
Imagine trying to reliably distribute a super high-frequency clock signal across a massive circuit board, or even just within a very large chip. Things like speed-of-light delays, transmission line losses, they make that exceedingly difficult, especially once you push past, say, around 66 millihertz on standard PCB traces.
Wow, okay, so physics gets in the way.
Physics gets in the way.
Yep.
And then you layer on Moore's law, billions of transistors, the demand for more speed, less power consumption. Well, designers have been pretty much compelled to incorporate multiple, often asynchronous clock domains within a single CPU, or SoC. It's the only way to get that optimized performance and better power management we expect now.
So you just couldn't build today's phones without this?
Pretty much, yeah.
Yeah.
You simply couldn't achieve today's device capabilities without it.
Yeah.
And what's really elegant here, I think, is the adoption of something called globally asynchronous DRASOS, locally synchronous architectures, GALS.
GALS, okay.
With GALS, the system isn't fighting against multiple clocks. It's actually designed from the ground up to embrace them.
Ah, so it's designed that way.
Exactly. You partition the system into these synchronous islands, each with its own clock, and these islands talk to each other asynchronously.
Okay.
And this approach, it brings significant benefits, like reduce electromagnetic interference, lower power consumption.
Yeah.
Because you avoid those huge current spikes you get with a single global clock trying to do everything at once. So in GLS, CDC isn't some side problem. It's really a foundational design philosophy.
So this invisible war against physics, these different time zones, how does it actually impact the devices in your pocket? Why should you, the listener, care that your phone or computer has these multi-speed parts?
Well, because it directly impacts the very things you value, right? The performance, the battery life, the overall stability of the devices we all rely on every single day.
The stability, yeah. Crashes.
Exactly. Without robust CDC, your phone would crash more, your data could get corrupted, your apps might just freeze randomly. It's really the silent enabler of modern electronics.
Okay, silent enabler. But there must be dangers. Let's talk about the specific danger that pops up when signals try to jump between these clock domains. You mentioned this tricky phenomenon called metastability. Metastability, even the word sounds unstable. So you described it like a tiny switch, a flip-flop, trying to sample data but getting stuck undecided between 0 and 1. How does that happen at a fundamental level?
Yeah.
That's precisely it. Metastability is when a digital system persists for sort of an unbounded amount of time in an unstable state, like balancing a pencil perfectly on its tip, you know?
Right, it can happen, but...
Exactly. But any tiny nudge sends it tumbling. In a flip-flop, this happens when the incoming data signal changes at precisely the wrong moment, right at, or extremely close to, the active clock edge that's trying to sample it.
A timing collision.
Timing collision, yeah. When that happens, the flip-flop's output doesn't immediately snap to a stable 0 or 1. Instead, it sort of hangs at an intermediate voltage level for an unpredictable amount of time before it finally resolves.
And what causes that collision?
The core cause is a violation of the flip-flop's fundamental timing rules, its setup and hold time requirements. Asynchronous inputs coming from a different clock domain, they're the prime culprits.
Okay.
But here's a really crucial detail. Even in designs that look perfect on paper, tiny variations during chip manufacturing.
Ah, the manufacturing part.
Yes. Those variations can subtly shift these timing windows. So you can get set up and hold violations after the chip is made, even if the design looks fine beforehand.
And when that flip-flop goes metastable...
Well, it can propagate incorrect or unpredictable data downstream. And the real nightmare is that these errors are notoriously hard to trace. They can lead to anything from system freezes, data corruption, to, in really extreme cases, even permanent chip damage.
Chip damage. Wow.
It's rare, but possible. And here's where it gets, well, a bit profound maybe. Metastability is inherently probabilistic.
Probabilistic, meaning you can't guarantee it won't happen.
Exactly. You can't eliminate it entirely. But what you can do is minimize its probability, make it incredibly unlikely.
Okay, so how do engineers deal with that? How do you quantify reliability if perfection isn't actually an option?
They use a metric called mean time between failures, or MTBF.
MTBF, right.
This isn't about guaranteeing 0 failures. It's about predicting the average time a synchronizer circuit is expected to operate without a failure.
Oh.
And the key insight, the really important part, is that the probability of a mid-Haskell state actually propagating downstream decreases exponentially with each extra flip-flop you add in a chain.
Exponentially. So adding just one more makes a huge difference.
A huge difference. So designers aren't really aiming for a bug-free system in the absolute sense. They're engineering for what we call a failure rate acceptable system.
Failure rate acceptable.
Yeah, where failures are so astronomically rare, they're practically non-existent for the lifetime of the device. It fundamentally shifts how we think about hardware reliability from perfect to, well, practically perfect.
So metastability is this core probabilistic issue. But when a signal gets stuck in that limbo state, what other kinds of errors can it trigger downstream? Are there sort of secondary ripple effects that can be just as bad?
Oh, absolutely. The ripple effects are significant. You're right. It's not just the initial metastable state.
It sounds like trying to catch a ghost that only appears at 3 a.m. on a Tuesday.
It can feel like that sometimes. Beyond the direct metastability, we face things like data loss.
Data loss. How?
This happens when a signal changes in the source domain, but just isn't successfully captured by the destination. Think of a really fast clock sending a quick pulse to a much slower clock.
Ah, the slow clock might just miss it.
Exactly. If that pulse isn't stable for long enough, or it's simply too short for the slower clock to even register it, poof, it's gone. Data lost. Then there's data incoherency. It's sometimes called reconvergence error.
Okay.
And this is a major headache, especially for multi-bit signals, like a data bus, say 8 bits wide.
Right, sending a whole byte at once.
Yeah. If each of those 8 bits is synchronized separately, and maybe some bits get delayed by a metastable event, while others zip through immediately.
Oh, so the receiving end gets a scrambled version.
Precisely. The destination logic sees an invalid or inconsistent combination of values, a mangled version of what was sent. If the downstream logic expects those bits to arrive in perfect lockstep, well, this leads to severe functional errors that are really hard to diagnose.
That sounds nasty.
It is. And then there are glitches and their propagation.
Glitches, like little spikes.
Exactly. Combinational logic, the parts that do adding, subtracting, that kind of thing, can sometimes generate these brief, spurious pulses. A glitch.
Okay.
Now, if such a glitch happens precisely within a flip-flop's sensitive timing window, it's set a hold window.
The flip-flop might think it's real data.
It can be mistakenly sampled as valid data. Yeah. Causing incorrect values, or even worse, it can induce metastability in that receiving flip-flop itself.
So a glitch can cause metastability too.
It can. Which is why these CDC bugs are often called silent killers.
Silent killers, because they're hard to find.
Because they're intermittent, they're unpredictable, and incredibly difficult to diagnose or reproduce consistently. They often slip right past traditional simulations.
Meaning you might not find them until the chip is actually made.
Exactly, leading to very costly chip respins or, the real nightmare, failures out in the field after the product is shipped.
All right, so we've unearthed these core problems, these silent killers. They sound genuinely terrifying for chip designers. So, given these challenges, what's actually being done about them? What are the clutter tricks engineers use?
Well, it's not so much tricks as it is a suite of really specialized synchronization techniques. For single-bit signals, just a simple on-off, zero.
The simplest case.
Right. The most common and pretty robust technique is the dual flip-flop synchronizer, often just called a 2FF synchronizer.
2 flip-flops. How does that work?
The mechanism is elegantly simple. You place 2 flip-flops, one after the other, back to back, in the destination clock domain. Both are clocked by that destination clock.
Okay.
The first flip-flop samples the asynchronous input signal coming from the other domain. Now, if it goes mistraceable,
Which it might. Huh.
the crucial part is that the second flip-flop samples the output of the first one after a full clock cycle of the destination clock has passed.
Ah, so it waits a cycle.
Exactly. That delay provides critical time, usually enough time for any metastable state in that first flip-flop to resolve itself into a stable, valid logic level, either 0 or 1.
So the second flip-flop gets clean data.
Hopefully, yes.
Yes.
The advantages are clear. It's highly effective for these single bits. It's simple to implement and very area efficient on the chip.
Sounds great. Any downsides?
Well, it does introduce latency, a minimum of 2 clock cycles of the destination clock.
Okay, a slight delay.
And remember, while it drastically reduces the probability of failure, it doesn't eliminate it entirely. That MTBS is finite, just hopefully incredibly long.
Right, the probabilistic nature again.
Exactly. And crucially, this 2FF method is absolutely not suitable for multi-bit data.
Why not?
Because it doesn't guarantee simultaneous synchronization of all the bits. You could end up with that data incoherency problem we just discussed.
Got it. So good for one bit, bad for many.
Precisely. And sometimes, for really critical signals needing even higher reliability, designers might use multi-stage synchronizers, 3FF, 4FF. Adding more stages exponentially increases that MTBF.
Okay, so that covers single bits. What about synchronizing those multi-bit signals, like that 8-bit bus example? That sounds much harder.
It is definitely more complex. We need different approaches.
Yeah.
One common method is using handshake protocols, often called request acknowledge or RECAC.
Handshaking, like a digital agreement.
Kinda, yeah. It's typically used when the clock frequencies aren't drastically different, or maybe when the destination clock is slower than the source.
How does it work?
It works like a polite conversation. The source puts the data on the bus, then it raises a request signal.
I have data for you.
Exactly. Then it patiently waits. It doesn't change the data until it gets an acknowledged signal back from the destination.
Okay, I got the data.
Right. Both that request signal and the acknowledged signal have to be properly synchronized across the clock domains themselves, usually using those 2FF synchronizers we just talked about.
Okay.
So the destination samples the data when it sees the synchronized request, and then it sends back the synchronized acknowledge.
What are the pros and cons of that?
Well, handshake protocols are generally very safe. They're generic. They guarantee data coherency, no scrambled bytes, and they work regardless of the specific clock frequencies.
Sounds good. The catch.
The catch is latency, big time, because you have this round-trip communication synchronizing signals in both directions. It takes time. This can really limit the bandwidth, the speed at which you can transfer data, not always suitable for high-speed stuff.
Right, that back and forth slows things down. So what if you do need high bandwidth or the clocks are wildly different speeds?
Then designers often turn to asynchronous first-in, first-out buffers, asynchronous FIFOs.
FIFO is like a data queue.
Exactly. Think of it as a smart data pipeline or buffer between the domains. It's often implemented using dual-port memory, like SRAM. Data gets written into the FIFO using the source clock, controlled by a write pointer, and it gets read out using the destination clock, controlled by a read pointer.
Okay, so it buffers the data. What's the tricky part?
The absolutely critical detail is how you synchronize those multi-bit read and write pointers between the domains.
The pointers themselves need crossing.
Yes. And if you just try to send the binary value of the pointer directly, remember binary 7 is 0111, binary 8 is 1000.
Right, multiple bits change at once.
Exactly. If the receiving clock samples that multi-bit pointer right when it's changing, You could grab a completely wrong, invalid pointer value,
Yeah.
catastrophic incoherency.
So how do you solve that?
The solution is ingenious. Binary to gray encoding.
Gray code. What's that?
Gray code is a special way of encoding numbers so that only one single bit changes between any two successive values.
Only one bit. How does that help?
It means even if the receiving clock samples the gray-coded pointer while it's transitioning, the worst that can happen is it gets the value immediately before or immediately after the transition. But since only one bit flipped, it's still a valid adjacent pointer value. It avoids those catastrophic jumps.
Wow. That's clever. So you convert the pointer to gray code, send that across the domains, and then convert it back.
Precisely. You synchronize the single-bit changing gray code pointer, usually with two FF synchronizers on each bit, and then convert it back to binary in the destination domain. It's a classic fundamental technique for reliable multi-bit CDC.
Okay, so FIFOs sound powerful. Advantages, disadvantages.
High bandwidth, definitely.
Yeah.
Excellent isolation between the clock domains. Great for handling large bursts of data.
Disadvantages.
They require more hardware resources, more chip area, more power compared to simpler methods, and they are inherently more complex to design correctly and, crucially, to verify. Plus, you need to carefully manage the FIFO's depth to prevent overflow writing too much data or underflow trying to read from an empty buffer.
Right, so more complex.
Definitely. And if we kind of zoom out for a second, selecting the right synchronization technique, it's never a one-size-fits-all thing. It's highly dependent on the specific needs. Data width, transfer rate, how much latency is acceptable, the resource budget. This often leads to what designers call a heterogeneous design approach within a single chip, using different CDC techniques in different places.
That's fascinating how they mix and match. Are there even more advanced, maybe more niche solutions being explored beyond these? What's a sort of bleeding edge look like?
Oh yeah, research is always ongoing. People are looking into things like adaptive synchronizers.
Yeah.
These try to dynamically adjust the latency based on current operating conditions.
Smart synchronizers.
Kind of. And speculative synchronizers, which essentially try to guess the data value early to reduce latency, and then have a mechanism to correct themselves if they guessed wrong.
Gambling on the data.
In a very controlled way. And another really significant area, especially relevant because of those manufacturing variations we talked about, is post-silicon error recovery methods.
Fixing things after the chip is made.
Exactly. Techniques like advanced clock path tuning. This allows engineers, after the chip is fabricated and tested, to precisely tweak the delay of the clock signal reaching specific flip-flops.
That is the help.
It can effectively shift the timing window to resolve those subtle setup time violations caused by manufacturing variations. It's shown amazing effectiveness, like over 99.99%, with only minor hardware overhead needed to enable the tuning. It's like having a final adjustment knob after the fact.
Wow, fixing hardware with timing tweaks. That's pretty cool. Okay, so you've gone through this incredibly complex design process. You've picked your FIFOs, your two FFs, maybe even some fancy handshake logic. How do you actually know it's all going to work reliably? You, the listener, probably just assume your phone will work. But for the designers, verifying these CDC paths sounds like a nightmare, especially if the bugs are, as you said, intermittent silent killers.
It is one of the biggest verification challenges, absolutely.
Yeah.
Traditional methods often fall short. For example, standard register transfer level or RTL simulations. They're great for checking basic functionality, but
they don't handle the randomness.
exactly. They typically run with fixed clock periods and don't accurately model the probabilistic nature of metastability or those tiny timing violations caused by, say, signal noise or voltage droop. This leaves what we call verification gaps. Bugs can just slip through undetected until you have silicon in hand.
Okay, so simulation isn't enough. What else?
Well, there's static timing analysis, STA, essential for synchronous designs.
Right.
But STA tools are designed for paths where timing is predictable. They can't directly analyze these asynchronous CDC paths properly. In fact, if you're not careful and tell the tool to ignore these paths using false path constraints,
You might hide a real problem.
worse, you might cause the synthesis tools, the tools that actually build the circuit, to make optimization decisions that physically break the CDC synchronizer circuit, thinking it's not important.
Ouch, okay. What about formal verification, using math to prove correctness?
Formal verification is incredibly powerful, yes. It can exhaustively check properties, but for large, complex chips, it often runs into the state-space explosion problem.
Too many possibilities to check.
Essentially, yes. The number of possible states that a design can be in becomes astronomically large, making a full chip proof computationally infeasible sometimes. So these limitations together mean CDC bugs often bypass conventional checks, resulting in, well, costly respins or those dreaded field failures.
So how do they tackle it then, if the standard tools have gaps?
It requires a dedicated, multi-pronged approach, a comprehensive CDC verification flow. It usually starts with static verification.
Static, meaning not running simulations.
Right. This involves specialized linting tools and structural analysis. These tools examine the design's code, the RTL itself, looking for structural red flags.
Like what kind of flags?
Things like missing synchronizers on paths that cross domains, or finding combinational logic placed incorrectly within a CDC path logic that could generate those glitches we talked about, or identifying potential reconvergence issues where signals split and recombine improperly across domains. And the beauty is, it finds these structural problems before you even run a simulation.
So cleaning up the structure first.
Exactly. It's a crucial early step. Then comes dynamic verification, but often enhanced.
Enhanced how?
Often by using metastability injection, or MSI.
Injecting instability on purpose.
Yes. It sounds counterintuitive, but it's powerful. Verification engineers use special simulation models or techniques to actively force flip-flops at CDC boundaries into potentially metastable states during simulation.
Why would you do that?
To stress the design, to see how the downstream logic behaves functionally when faced with that unpredictable settling time. It deliberately exercises the design under the very conditions that cause these probabilistic bugs, hopefully fleshing out errors that a normal, clean simulation would completely miss.
Okay, that makes sense. Forcing the weird cases.
Right. And finally, there's formal verification used strategically.
Despite the state space issue.
Yes. It's often applied to prove the correctness of specific critical CDC paths, or the protocols used in things like FIFOs or handshake logic, especially within reusable IP blocks. Techniques like assertion-based verification, or ABV, use formal properties, often written in system Verilog assertions, to define exactly how a CDC protocol must behave and then mathematically prove it holds.
Okay, and for the whole chip?
For massive sockets, designers typically use hierarchical CDC verification. You rigorously verify the individual IP blocks first, maybe using formal methods extensively there. Then you create simplified sign-off abstract models, or SAMs, those blocks.
Abstract models.
Yeah, models that capture just the essential CDC interface behavior without all the internal complexity. This allows for more efficient SOSI-level verification, checking how the blocks interact without hitting that state space explosion quite so hard.
So verify the pieces, then verify the connections.
That's the gist. And advanced techniques like counterexample guided abstraction refinement, CGAR, help manage complexity in formal tools, making proofs more achievable. It's really become quite a science.
So it sounds like the goal has shifted. It's not just about finding bugs anymore. It's more about building this incredibly high level of confidence in the design's overall robustness, specifically by managing that inherent probabilistic nature of metastability itself.
You've nailed it. It's a shift from striving for, is it perfect, which is often impossible with CDC, to, is it practically perfect?
Yeah.
Is the probability of failure so low that it's acceptable for the product's lifetime and requirements?
Okay, so for the designers listening, the ones actually building the next generation of these complex systems, what are the golden rules? What are the absolute must-follow best practices to conquer CDC?
Right, rule number one is probably minimize CDC paths wherever you possibly can. Fewer crossings mean a simpler design, fewer potential points of failure, less to worry about, less to verify.
Makes sense. Keep it simple.
Then, proper synchronization is just non-negotiable. You must use an appropriate synchronizer for every single asynchronous input and every CDC path, no exceptions. And critically, choose the right technique for the job, 2FF for single bits, something else for multi-bit, considering the clock relationship.
No cutting corners there.
Absolutely not. Also, strictly avoid combinational logic in CDC paths. That means no logic gates sitting directly between the synchronizing flip-flops where they could inject glitches right before the signal gets captured. Keep that path clean.
Okay.
For multi-bit signals, the mantra is single point of synchronization. Treat the entire bus as one unit. Synchronize it coherently using techniques like handshakes or those asynchronous FIFOs with the gray code pointers. That's key to preventing data incoherency.
Got it. Handle the whole bus together.
Yeah. And then there's proper timing constraints. These are instructions you give to the synthesis and place and route tools. They need to be accurate and comprehensive to guide the tools correctly, especially making sure they don't incorrectly assume a CDC path is a false path and optimize it away.
Tell the tools the truth about the CDC paths.
Exactly. For large designs, hierarchical design really helps. Breaking the system into smaller, manageable submodules makes implementing and verifying CDC much less daunting.
Divide and conquer.
Right. And finally, something often overlooked but vital: comprehensive documentation. Keep clear records of all the clock domains where every CDC path is and exactly which synchronization technique was used and why. It's crucial for maintenance, debugging, and future reuse.
Good documentation saves sanity later.
Absolutely.
And looking forward now, sort of gazing into the crystal ball, what's coming next in CDC management? How are engineers going to keep pushing the boundaries here? Are there new challenges or new solutions on the horizon?
Oh, definitely. The field is always evolving. We'll certainly see continued research into advanced synchronizer architectures.
Yeah.
Things like those adaptive and speculative synchronizers aiming for lower latency or better power efficiency.
Smarter synchronizers becoming mainstream.
Potentially, yeah. There's also a lot of interest in applying AI and machine learning and verification.
AI for finding CDC bugs.
Yes, potentially using ML to identify complex failure patterns in simulation logs or static analysis results that humans might miss, or just to make the whole verification process more efficient.
Interesting.
We'll also see further development of enhanced post-silicon recovery methods, like more sophisticated versions of that clock path tuning, giving designers more levers to pull after manufacturing to compensate for variability.
More knobs to tweak after the fact.
Pretty much. The drive for power efficiency and performance scaling means we'll likely see continued adoption of GLS architectures, which, as we said, puts robust CDC solutions front and center.
Makes sense.
And the scope is broadening, too. There's a trend towards system-level synchronization, looking beyond just paths on a single chip to synchronizing clocks and counters across multiple boards, essential for really complex systems like quantum control setups.
Wow, synchronizing across boards.
Yeah. And within verification, there's a push for more comprehensive coverage models, better metrics to actually quantify how thoroughly the CDC aspects have been verified, trying to definitively answer that question. Is my CDC verification done?
Moving beyond just bug hunting to proving coverage.
Exactly. And finally, I think we'll continue to see tighter tool integration, more seamless flows between the static analysis tools, the dynamic simulation tools, including MSI, and the formal verification tools, making the whole CDC sign-off process smoother and more reliable.
A more unified toolkit.
That's the goal.
We're at an incredible deep dive. We've really gone through the weeds on a crucial, yet, like you said, often unseen aspect of digital design. We've unpacked how clock domain crossing is just this unavoidable reality in modern chips.
Absolutely fundamental.
How metastability is that core probabilistic challenge at the heart of it.
The ghost in the machine, almost.
Yeah. And how brilliant engineering solutions, from those simple little 2 flip-flop synchronizers all the way up to complex FIFOs using that clever gray code trick, manage these probabilities to make sure our devices actually work reliably.
And, the constant innovation here in managing CDC, it really highlights something important. Digital design isn't just about building faster chips anymore.
Right.
It's equally, maybe even more so, about building smarter and fundamentally more resilient systems, even when you're up against these basic physical challenges and probabilities. It's really a testament to the fact that there's always more to learn, always more to optimize.
Pushing those boundaries constantly.
Constantly.
And so for you, the person listening, relying on these devices every single day, maybe the takeaway is this. Next time you tap on your smartphone screen or fire up your computer, you'll know a little bit more about the incredible, often invisible engineering happening under the hood. The constant battle against physics and probability that makes it all function so seamlessly. It truly has been a deep dive into the hidden, complex, and fascinating world of clock domain crossing.